This is one of the Japanese paper balloons, identified by the code name Paper. The unit carries up to 4 10-pound incendiaries and a central payload of about 60 pounds of incendiaries or anti-personnel HE bombs to drop on the west coast of the United States and Canada. It is then supposed to destroy itself. Several defective units, however, have come to Earth at various locations. Some of these have been recovered, sufficiently complete for detailed analysis and investigation. Back plots from available data indicate that the balloons are released in Japan, probably from the Nagoya district, at about 30,000 feet under prevailing wind conditions reaching velocities of about 100 miles per hour. It takes approximately 4 days to make the crossing during the winter months, when wind velocities are highest. During the rest of the year, velocities drop so greatly that a successful balloon crossing would be rare. These units have been found in areas ranging from Alaska all the way south to the Mexican border. The balloon unit has a paper gas bag, 64 rope shrouds about 40 feet long, and an automatic ballasting and firing control. The ballast consists of sand in paper bags. The payload is usually made up of incendiaries and possibly one or more anti-personnel HE bombs. The material of the bag is 5-ply rice paper, about 8/10,000ths of an inch thick. Paper strength is 69 pounds per linear inch when dry and about 37 pounds per linear inch when wet. It has 1/10 the permeability of American rubberized balloon fabric. When the bag is inflated, the paper has a load of only 7 pounds per linear inch, or 1/5 the strength of the paper. The total weight of the bag is about 150 pounds. The bag is 33 feet in diameter and holds 17,500 cubic feet of hydrogen gas. The escape valve is of the single disc type, 17 inches in diameter. It is made of pressed steel and has a rubber gasket for a seal. Pressure is regulated by a spring. Release pressure is set for 9/10 of an ounce per square inch. The valve is mounted on a 3-leg spider bracket. This is the business end of the balloon, an extremely ingenious device for maintaining a fixed altitude of 30,000 feet and for dropping the payload. It consists of an electrical source, a demolition block, a box containing 4 aneroids, fuse jacks, switches, blowout plugs which support the bags used for ballast, incendiaries, and a central payload. The ballast drops away in this manner. Sandbags, incendiaries, and central payload are suspended by means of T-hooks which fit between the blowout plugs. Though they are intended to fire in pairs, blowing either one releases the T-hook. Let's take this ballasting control mechanism apart and see how it's made up. First, the fuse to the demolition block is pulled out. Then the plug from the battery to the aneroid is disconnected. Now, both the battery box and demolition block can be lifted out. Here is the platform on which the battery box and demolition block made their Pacific crossing. The demolition charge is a 2 1/2 pound block of picric acid detonated by a fuse. This charge is supposed to destroy the ballasting mechanism. The battery case consists of 3 celluloid-like boxes, and airspace provides some thermal insulation. A 20% solution of calcium chloride in the middle box acts as a thermal overcoat and is sealed by a rubber plug. The solution helps to ward off freezing of the battery at night and excess heating during the day. The battery within a third box puts out 2 volts and about 10 amps on short circuit. It is a lead-acid wet cell type with 5 plates. Spacers maintain a uniform airspace between the outer boxes. The aneroid plate is now taken out. These are the aneroid barometers. The master aneroid is in the center of the board. The 4 aneroids are connected to the battery by wire leads. This aneroid is set for about 27,000 feet. The setting can be adjusted by turning this screw. This one is set for about 20,000 feet. It works on a straight make and break contact and can also be adjusted. This one is set for between 13,000 and 20,000 feet and controls only the payload. The master aneroid, covered with a cap, controls the dropping of the ballast. Unlike the other 3, it does not close the circuit at a fixed altitude, but only when a preset pressure decrease occurs. These are the aneroid bellows, which expand with a decrease in pressure. Attached to the bellows is this post, which, in turn, moves the arm through contact at this friction clutch. The arm is pivoted here. When the post rises, the arm is raised, and the contact is opened. When the bellows pull the post downward, the arm closes this contact. Some of the units are different in that all aneroids are covered instead of just the master aneroid, as on the board to the left, as a further protection against weather, no doubt. In addition, some covers have a triangle painted on them. The aneroid marked with a triangle is wired in series with the other aneroids and is set to remain open up to 8,500 feet before it makes a contact. This is undoubtedly for additional safety in launching. The difference is easily detected because the contact rod is above the contact loop. When the balloon is launched in Japan, this plug is pulled, igniting the long launching fuse, which takes about 55 minutes to burn through to the first jack plugs. During this time, the balloon ascends rapidly until it reaches 30,000 feet, its operating altitude, and starts eastward. When the fuse burns out, this jack plug blows, closing switches and arming the number 1 ballasting plug. master aneroid is now in control. As the balloon loses some of its lift, say on the second night out, and descends, the master aneroid establishes electrical contact when the balloon has dropped about 2,700 feet. This contact causes the ballasting plugs to blow, dropping the sandbags suspended between the two plugs in number 1 position. Again, the balloon goes back up to operating altitude. Here is a chart of the electrical and fuse circuits. This is the battery. This master aneroid completes the circuit when the balloon drops 2,700 feet from operating altitude. Should the master aneroid fail, this one takes over and makes contact at 27,000 feet. Should both fail, this aneroid will close the circuit at 20,000 feet. These switches close when the fuse ends blow out of the upper aluminum ring and arm the electrical circuit. The number 1 plugs are ready to fire. When the balloon is launched, all circuits remain open until this launching fuse, burning at 102 seconds per foot, burns through and arms the number 1 switch. This allows the balloon 55 minutes to reach operating altitude. In time, when the balloon loses lift and descends, the controlling aneroid makes contact, causing the number 1 plugs to blow, drop ballast, and ignite timing fuses to arm the next switch. The blowout plugs and the timing fuses ignited by them have been quite carefully worked out by their Japanese makers. The blowout plug, shown here in cutaway section, consists of a chamber for the powder which blows the plug from the ring. This is connected by a small hole to the squib chamber. The powder charge is covered by tin foil and shellac to form a moisture seal. The powder consists of 96% potassium nitrate and 4% sulfur. The squibs function on the same principle as American squibs, but are much more complicated in construction. The flame from the squib passes through the small connecting hole. Thus the powder burns relatively slowly from the center to the outside. The plugs are eased out, and the rocking of the ballast unit is minimized. The powder flame from the plug ignites the timing fuse leading to the next jack switch. The brass fuse connections are vented for escape of gases. These vents are also moisture sealed. These fuses burn at the rate of 70 seconds per foot and require 2 1/4 minutes to burn through. This allows the balloon time to rise above operating altitude. The fuse finally ignites the powder charge in this chamber of the jack switch connection. That mass production of these units is probably underway or contemplated is shown by the presence in later units of permanent mold cast aluminum plugs instead of the older, completely machined steel plugs. The design of the plug has not been changed. When the plugs blow, the squib leads are severed. This prevents one set of plugs from short-circuiting the next plug. The flash ignites the fuses behind these holes. From the number 1 plugs, the fuses burn to the number 2 jack switches on the opposite side of the ring. These blow, permitting the jack switches to close and arming the number 2 ballast plug. When the balloon has again dropped a preset distance, the master aneroid makes contact and the number 2 plugs blow. The released ballast permits the balloon to rise again to operating altitude. Meanwhile, the blowing of the plugs has ignited the fuses to the number 3 jack switches on the opposite side of the ring. When these jacks blow, the number 3 ballast plugs will be armed. Fuse leads are ignited by the number 1 plugs. The 2 1/4 minutes of burning give the balloon time to rise to operating altitude. The number 2 switch closes and arms the number 2 plugs. When another loss of altitude occurs, the circuit will then be completed through the battery and an aneroid, blowing the number 2 plugs, and again igniting timing fuses. This process continues through numbers 3, 4, 5, 6, 7, and 8. However, when the number 9 jack switch is closed, this arms not only number 9 plugs, but also one of the plugs supporting the payload. Should any pair of fuses between 9 and 36 fail to perform, no ballast can be dropped and the balloon will descend. This aneroid will then close a contact at 13,000 feet, blowing a plug to drop the payload and igniting the fuse to the demolition block to blow up the whole ballasting unit. The payload is fastened to this T-hook and suspended from these 2 blowout plugs in the bottom center of the ballasting ring. When either plug blows, the T-hook is released and the payload falls away. The blowing of the payload plug in the number 9 circuit also ignites the fuse leading to the demolition block. On some balloon units recovered, the demolition block has been found not beside the battery on top of the aneroid box, but within the ballasting ring, the logical place for it to do the most destruction to the unit. This region is also a good location in which to look for booby traps. In the event one of these units is found, do these 2 things to render it harmless, provided no fuses are smoking. First, rip or pull the fuse from the demolition block. Second, unplug the battery lead. If the fuses are smoking, stay away. The circuits from 9 to 36 operate the same as 1 and 2, except for 36, which, like number 9, has a double duty to perform. Not only are the number 36 ballast plugs armed, but also the other payload plug in the center is armed. If all fuses function as intended, the payload dropping will be controlled by these aneroids. When the plug blows, a fuse to the magnesium flash charge on the balloon is ignited. In an attempt to ensure destruction, a flash hole connects the payload blowout plug recesses. The hope is that should either plug blow, the other will be ignited and both fuses will function simultaneously. This is the 4th day out, and as the last sandbag is dropped, only the payload remains. Presumably, the lighter-than-air invader is now over our coast. The first incendiary is dropped. There goes the 4th one. Now only the central payload is left. Note that it is suspended from the usual T by means of an S hook. payload is dropped, and the fuse is burning to the demolition block, which will destroy the ballast control unit. At the same time, the fuse leading to magnesium flare is burning. Freed of the weight of the ballast control unit, the bag sails up to higher altitudes, where the magnesium flare will ignite the highly inflammable hydrogen. Such are the facts about this ingenious menace. It may come over in larger and larger numbers. Its makeup may change. It may be larger and more destructive than at present. It can be detected by radar or reported by ship and aircraft lookouts. Defensive measures by all services are in operation to meet this menace.